presenting two allied papers, as you already know from the notification, both from the same group, both following the same thought process of scattering transform, which was also briefly discussed in the last talk by Mikkel. So we will just start with the application of this deep scattering transform to audio application. This is slightly older paper, older in the sense it's around 2014 and so on. But it had interesting applications and it's in audio, so I thought this would give you a better feel before we go on to generalize the thought process of scattering as developed by Mallat. So this work was jointly done by Joakim Anden, who was, I met him in one of the conferences. He was in KTH apparently, in this department many years ago. Now he's in Simon's University in the US after working with Mallat. Yeah.
Was he here? No.
I don't know, he seems to...
I can hear it's a Swedish name, but I don't remember...
So there's an E here, and he seems to know Joakim.
Okay, yeah, perhaps he was with computer science. Oh yeah, okay, I can find them. Yeah. I don't remember.
But now he's settled in the US for a few years. So what exactly is this work about? So it's about a particular specific application, that is the Mel frequency capsular coefficients, which you don't need to worry. I'll just give you a brief idea. That's all we need for now. So basic context here is audio classification, which includes timbre classification, pitch, other features like melody, beat, pattern, and everything. So that is a general audio classification scene. And what is popularly used is the Mel frequency capsular coefficients, which is based on reordering of the short time Fourier coefficients. So I'll just come to that later. So what is ideally asked for, or what is desirable in audio classification, is that you not only maintain local features but also long time features, because beats typically are long time features and something like a sharp attack is a short time feature. So you want a feature vector for this particular sample which can capture all this information. And it turns out that MFCC, which is popularly used for this purpose even today, actually does a pretty good job locally, but if you increase the time scales, if you want to have more features, long-term features, it becomes lossy and starts losing a lot of information. And this has connections in a way to the deep scattering spectrum. That is why this work. And what they show is that using the deep wavelet architecture that is developed, you can show that MFCC is nothing but only taking one part of the tree, of the wavelet tree, and you would do much better if you take the whole tree. So that is roughly what is happening here. So yes, and in audio classification you also need the invariance to certain features. One of the features is the frequency, so at what bass pitch the song is sung, for example, should not matter. Okay, let's get into that. But before that, I will just give briefly a very basic overview of Fourier transform, which I don't think is needed here, but anyway, to be in the spirit. And the short time Fourier transform and the Wavelet transform. And then we will discuss the MFCC and what is exactly this work all about. So, as we all know, the Fourier transform is basically expressing a signal, a time, let's say time, so we are dealing with audio signal, so a time signal in terms of its frequency component. So when you take the Fourier transform, you get an idea of the frequency components en masse, but you don't have the localization information anymore. So I'm just giving you a hint to what comes later. So yes, and the Fourier amplitude, so if you shift the signal in time, it manifests as a phase delay in the Fourier spectrum. So like so coming back to the audio classification, it should not matter if I started at 1 second or 10 seconds if the same song is repeated. But if you just see the Fourier transform, it has changed. So if you want to get rid of that translation, what you do, just take an absolute value. So the C has vanished, and now you have a basic feature which is invariant to shifts. Okay, this is basically one of the fundamental ideas which will go on extending all through the work. So now this is a very simple case. In practice, you have something like what is called warping. So uneven shifts at different parts. So the same song might be sung by you and me, but with different speeds at different parts. So you don't have exactly a shift, but you have something which is more. So you can model it as t minus tau of t. So it's a time varying shift. I don't have that expression here, but anyway. So in that case also you want the signal to be invariant. So if it is not too varying but still warping, even then you want it to be invariant. But unfortunately the Fourier transform does not do that. So although the low frequencies do not get very upset when I am actually doing this, if it's not too rapid, the change. So the Fourier transform of this and the Fourier transform of this agree, as I will show in an example, for low frequency content. But the moment you look at the high frequency content, it has shifted too much for a very small shift or highest shift. Okay. Yeah, and now as I said, the Fourier transform actually takes away all the time information. So what is a natural way out, if you want also the time information, is to make the signal into chunks of time. So what you do is you take this whole signal, chop it into chunks, window it, and then take the Fourier transform. So you're as if taking chunk by chunk Fourier transform. So now you have a Fourier transform which has some relation to the chunk. So now you have a time frequency picture, and that's nothing but the short time Fourier transform, because you're taking short time frames. And the absolute value or the modulus of the short time Fourier transform is called as the spectrogram, which gives you a time frequency picture. So the signal, if for example, so let's say the frequency, this is the signal, so it's frequency has increased over time. If you just take the Fourier transform, it will be a smudge showing all the Fourier frequencies. But if you take an STFT, it will actually show, if it's a chill like this, it will actually show you that both the time and the frequency information. So which is why spectrogram is important. Yes. But notice the problem that I mentioned earlier is that you can show that the high frequency components are too much disturbed by the Fourier transform. So that property also is inherited by this short time Fourier transform, because it's in turn you are doing the same Fourier transform but on chunks. So you will still have the problem that the high frequency will shift too much even if you have shifted a little bit or used a bit of warping in the time. And this is something which we want to avoid. So we want a transform which does this time frequency tiling, because we want both information, but does it in a manner which is robust to small diffeomorphisms or translations or scaling within time. So what is such a transform? One of the wonderful transforms that actually does this probably is the Wavelet transform, and that is something Mallat and his group almost originated right from the beginning. So what is a Wavelet transform? Wavelet transform is basically instead of using sinusoids as your basis, you use localized, time localized bumps, which are basically bandpass signals. So bandpass filter. So a wavelet transform's frequency response is something like this. So these are the different wavelets, and they have all been derived by dilating a basic template called the mother wavelet. So you stretch this guy in frequency, which means contracting in time. You stretch and dilate and contract, you get all these from, well, you can start as a mother wavelet as any of them, and you can stretch by a factor and you get something that spans the entire space. And why do you want this kind of structure? So what am I saying? I'm saying that the analysis window in frequency should be large as you go to the higher frequency end. What does that mean? Since the spread in time and frequency are inversely related, what I'm asking is that in time I'm looking for shorter and shorter windows. Does that make sense? It makes sense because if you want to analyze something which is fastly varying, like a sudden beat, if you want to get this in addition to everything, you must look at this chunk, or you must look at a window which is short, which in turn transforms to looking at a big window in the frequency. And why is that? Because a sudden change like this is a high frequency component. So it makes intuitive to ask that slowly varying things you can wait for a long time and then analyze, or you have the analysis window which is large. And if you have shorter time activity, you must have a shorter time window. So that is basically one of the basic intuitions behind such a transform, which has this kind of time frequencies tiling. So if you analyze everything in time domain, you have nothing left of frequency. You can take the Fourier transform, you have nothing left of time, you just have the frequency and the amplitude. You take this short time Fourier transform, which is also known as the Gabor transform, and you have a time frequency picture, but it's like this. So it's you're moving the same window in time and frequency. But like I said, you want something which is more like this. So at shorter intervals, you must have a different time frequency scaling. Okay, and this is precisely achieved by this kind of bandpass filter setup. You can ask me a question whenever you feel stuck. So just to give a picture, so what am I doing? These are the bumps, so these are the wavelets. So these are localized in time, so they have a finite support in time and frequency. That's why you have this kind of tiling. So I take this, I stretch it, I stretch it, I stretch it. So I have all the stretched versions of this particular mother wavelet or template, and I correlate the signal with that, and my wavelet coefficients is nothing but the convolution with these guys. So what am I doing? I am doing a matched filtering with each of these. So as you have, when the scale, so the scale is the extension or the scale factor by which I dilate and contract this mother wavelet. So if you have very short support versions, this will pick up the instantaneous activity more than the others. Right? So different scalings will pick up different kinds of activity. So you have a multi-scale behavior. It's because that's natural also, because we have this interpretation or this picture of this bandpass filters. Right? So different filters, different scalings will pick up different frequency components. So coming, a wavelet transform is basically breaking down the signal into a low pass and a high pass set of band pass filter components.
Looks like your battery.
I need to get it there.
Yeah, if you want, I can make it. Thanks. You're on the track. Keep going. Don't worry. I'll be back in a minute.
So now we go to the Mel frequency capsule coefficient. So what is this mel frequency capture coefficient. Before that, I will just show that example where. So here the blue one is, so this is the frequency picture of a time signal. So it's a harmonic signal with 3 harmonics. Okay. So the blue one is a basic xt, and I have just disturbed it by xt to xt minus tau t, which is a small disturbance, but slowly varying. So if you see this is the Fourier transform. These are the Fourier transform of the initial xt. The red one corresponds to the shifted or the warped version. What do you see? You see that although, I mean, in principle, by intuition, these are close enough, so you should expect the transform should be close. You see that it's close in low frequency, but as you go up the frequency ladder, the thing gets further and further spaced apart. So if you take a L2 norm here, for example, it will be very large, although that's not the case by what you expect. Right? So you want, and why is this happening? Because you have harmonics. So here, so let the signal be a harmonic signal. So you have this harmonic multiples of this quantity, chi t thing. So when you shift it by epsilon, it gets multiplied by epsilon here, and the higher the harmonic, the more far spaced it gets. So that's why the problem with the Fourier transform. So this was to demonstrate that. So you want a transform or a feature vector phi, which basically does this, right? If I do, as I said, if I don't move this a lot, the movement of the feature vector should also be not quite a lot. So I want something which is in a way ellipsis continuous to this warping factor. So I would ideally want something like this. So if it's not too rapidly changing, so then this is almost close to 0, and then or these, even after shifting, the feature should be same or very close, similar. But if the Fourier transform, unfortunately, like we showed or we saw, does not do that, it very easily gives away in the, as you go up the high frequencies. So what MFCC does is, it actually couples the Fourier frequencies. So if you, it will actually couple the high frequencies into a bandpass picture like this. So what will happen if I now shift in time? This guy is shifted too, but not so much, because there is still overlap. So if I So if this was the initial picture, if I shifted it a bit, so this would remain close to epsilon, but this will start moving more and more. So now you have this, basically there will be no overlap at all. So what is the way? If you have so this is what happens if you have this expression of the signal or in the basis which is, all sinusoids. But if you have a basis which is this way, that is, you are expressing it in a basis like this instead of the line spectrum. If you move this a bit by epsilon, you still have significant overlap. Okay? So that's why a picture like this, now suppose this was the frequency picture of xt. Now if I shift by the same argument a bit squiggle in time, these guys will still have significant overlap. What was the problem with the Fourier transform is that this overlap quickly goes to 0. Right? There is no overlap, so the error quickly increases at the high frequencies. But now if you sort of chunk in on the frequencies, so that you have a filter picture like this, so then the movement, as you move from xt to xt shifted, there is still overlap and there's not much of a movement. So this is basically what the Mel frequency does. So it does not use all Fourier coefficients as such. It couples certain Fourier coefficients, or which is in effect doing something like this. Okay. And this is also motivated, in principle, how it started was to modeling the characteristics of the ear. So this sort of models how we perceive sound. We don't perceive all sounds in an equal frequency manner, but more in the manner like this. But coming back to the Mel frequency, so Mel frequency is still a time frequency or a time scale picture of the signal. Why is it the scale? I mean, instead of using all frequencies, I have lumped them together to form different bands. So what you can show is that in the end, although you are lumping together these bands, the Mel frequency is actually filtering out each of the band output. So you have you separate the signal into these bands, so they are all different frequency signals. But what Mel frequency finally does is filters them, all of these components with the low pass filtering. So there is a smoothing effect, or there is loss of information. So that actually you can show that the Mel frequency is doing something like this. So it's convolving the signal with a band pass filter, and the output is, so this is how it's defined. There is amplitude involved in the Mel frequency coefficients. You take the amplitude and then you filter it. Okay, so this, if you had maintained, you have for all bands. But now the moment you are filtering out, you are losing information. So you are only keeping a sort of blurred version of information from each of the bands. And that is why when you go to higher and higher frequencies, the MFCC starts losing a lot of information, because it's only keeping the low pass version of this. So then you come back to the scattering transform. The scattering transform, if you remember from last time, or well, we can just recollect. What does it do? It basically takes the wavelet transform, takes the amplitude, filters it. But this is one part. This is the sort of low pass part of this band pass component. What happens to the rest? So this is the low pass. So you have this low pass part, but what about this? You need this as well. So that is when you take the rest of the bands of the wavelet. Okay, so you keep doing it in a tree manner. You take the signal, you take the wavelet transform, which means you're taking a band pass filter version of the signal. You take the amplitude. Why do you take the amplitude? Is to make it invariant to some extent. Because if you just take the band pass filter component directly, it will have a lot of oscillations. So you want to reduce that degree of freedom, so you take the amplitude. You take the amplitude and then you low pass filter it. Why do you low pass filter it? So if you have translation in signal, as I said, what is the easiest way to kill the translation? Take the average. So if you have that local information here, 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 and if you want a feature which is invariant to the exact position, what do? Just take the average. So it will spread it all over. So that is exactly what is happening here. Okay, so this will spread out the variations. So you continue doing that. So you have this component. Now you take another wavelet on this, take the amplitude and take the filter coefficient. So let's see. So this is in effect what you're doing. So you take this signal, you take its low pass component, you take it out, and you have the rest of the high frequency or the band pass components. Okay, and each of those components you further take the amplitude, and then again do the same business, that you again split it into multiple bands, and you keep on doing this again and again. So what are you effectively doing? You are effectively transforming all the information into a low pass chain, because continually you are taking the low pass filter on each of these. So you are not letting go of information in any manner. So what MFCC did was to only keep this chain, the low pass details only, if you go back. But what the scattering or the fuller tree is doing is that you're keeping all information, not just low pass but high pass also, but you are transforming it in a way that everything is a low pass version. So you are not losing any of the information. And this naturally gives rise to a tree. And because it's a wavelet and it's in the form of convolutions, all these layers, you're basically doing convolution with filters, bandpass filters. So this naturally gives rise to a convolution structure, convolution deep network. But the good thing about this is that you're not learning. So actually what they showed is that if you finally collect all these features and use it for classification, you can actually get performance as good as trained neural networks, which is a bit interesting, because when you train you have a lot of troubles, like back propagation does not converge, you have gradient descent and everything. But what this is in a way describing what a trained neural network might be doing. So because this is also doing convolutions, this is also trying to bring invariance at every level. So when you're taking the amplitude and low pass filtering, you're killing invariance as a level after level. So this was an attempt to explain also what might be going on in general deep networks, as in what, because general deep networks are known to have this invariances at each level, that such to the extent that there are examples which I will show in the next part, where you have features corresponding to a person with just the face and another person with a spectacle. You do a minus of these features and then you add a face of another person. You get output as that last person with spectacles or something. I might have changed the signs. But the point is that it is known that deep networks tend to capture information in sort of invariant or linearized manner, and the deep spectrum or the deep scattering transform, what it does is an attempt to explain what might be going on, because this is exactly of the same form as the convolutional network, that has convolution at layer after layer, just that you're not learning transform. So you have a non-linearity here and you have a linear map here. So what is the general structure? You have a convolutional layer formed by a non-linearity and so on. So this follows that structure, but nowhere do you learn something from the signal. And then it is shown that this feature is actually abiding by what we wanted in the beginning, that it actually does not get too upset if you change it from xt to x shifted or time warp, that is, you're introducing a diffeomorphism. And this was for 1D, so this was an application in relation to 1D signal. We will just finish this and then go to the general version. So what they finally do is that use this feature, take the log and then you feed it to a classifier, that standard classifier is just SVM. So use this as a feature vector to make the classification between different audio signals, and that seems to work or even outperform the state-of-the-art audio classification techniques. So this here ends the first article, that is a deep scattering spectrum. Any doubts, comments, questions?
When was the year of publishing this?
This was in 2014, and after that there was a horde of literature following similar ideas, but they are all in the basic template.
So there is no pooling, no biases to.
No. So I will discuss some other some other aspects when you come to general signals, which is the next or the latest article or the next talk or subtopic. But in this framework, which they have applied not just to audio but also to say ECG and other fetal rate monitoring and so many other standard 1D, what you can call 1D signal analysis, they have applied it to all these places and shown that it does quite well. And you're not learning anything, so there is no pooling. At least this is more or less verbatim done in a lot of their articles in the 1D signal domain. And what they show, there are other interesting things which is to some extent intuitive, is that as you go on increasing the layer, the information gets lesser and lesser, and it's already known that wavelet, by the way we have defined, it captures things sparsely, so it will only capture activity which is relevant to its own scale. So if you look at these coefficients, they are already sparse. So, and the wavelet is actually has a nested structure. So wavelet at a particular scale can be, there are certain wavelets where you can express a wavelet at, so the simplest is a Haar wavelet. So this is the Haar wavelet. This is a simple bandpass filter. This is one of the simplest wavelet structures. So I scale it down or scale it up, I will get this. Right? So what this wavelet can be actually expressed by summing these wavelets and further down and so on. So actually this structure is also used to get this done very quickly. So it's like a DFT, for example. It's like fast wavelet transform. So you don't have to actually compute all the wavelet coefficients independently. You can actually do it in a fast manner. You can actually, what is done is, one of the things is dyadic. So you first split the signal into a high pass, low pass, then do high pass, low pass and high pass, low pass, like this. So you eventually end up in the constant Q structure that I mentioned. So that is done, and they also exploit to some extent the sparsity in some of the applications, that the wavelet coefficients will be sparse. But they do not use pooling or any other dropout. I mean, there is nothing to drop out here, there is no learning.
But the most relevant for me was that there is no biasing at any point. So you have the non-linearity, that it's always at the initial zero. So there's no a plus B anyway.
No.
Okay.
So it's just a simple just the absolute value here, but they have also, I think, done some other non-linearity. But this is what is usually used, the absolute value. And this already is proven to be contracting and everything. So the absolute value is already contracting. So if x and x dash are not too far apart, then the wavelet modulus coefficients or the tree coefficients will not be far apart. Why is this important? Because if you disturb by a little bit of noise, your features will not get too disturbed. But this is not the case in general learned deep network. So there are examples where you just add a little bit of noise and everything gets upset. So that way this is you have better control over what is happening here. Some of the nice properties.
So neural networks that doesn't hold, in deep neural networks, this kind of, what do you call it, stability.
Yeah.
This does not necessarily hold.
In general learned networks.
Yeah, where you have like, exactly, I mean, where you have learning going on basically.
No, actually there is this whole generative adversarial networks field which has come into play just because of this, that you had a very small epsilon and error,
Yeah.
and you basically feed the same image as input, you don't get back anything similar. It's
Right.
vaguely
Yeah.
different. So this has raised questions on how reliable it is or secure this whole learning business is.
Yeah.
So that way I think probably this is better, but this actually in practice the coefficients decay very quickly, or you can show in some cases almost exponentially. So
Right.
in practice you will not use more than 4 or 5 layers of this, because you have already contracted most information
Yeah.
that because of the structure like this.
Right. And then this is like, this works actually for any 1D signal basically.
Yes,
Yeah.
actually
And
any
So
signal
we
for
only
that
have,
matter.
yeah, so basically the only thing you have to change basically is like maybe the number of layers. So if you're testing this on image, or no, not image, like if EEG data versus voice recognition, the only thing maybe you have to change is like how
Yes,
deep,
yes.
yeah.
So in fact the same thing applies to image, 3D volume data,
Yeah,
all kinds of data, because I mean 2D higher dimension is just stacking up in a way, or yes.
yeah, right.
So the same thing holds there as well. But I think yes, in practice what differs is the number of layers you use. That nobody can fix beforehand, but at least in the audio case they had some heuristics saying that after a point you will know, or I think they tested out and found that after for signals of beyond this frequency, after 3 or 4 layers it does not matter.
Doesn't matter.
But
Right.
it matters in reconstruction. So it matters, it does not matter in classification, but if you want to reconstruct, this is not necessarily invertible. In fact, it is not invertible in general, because it's not convex, it's nothing nice mathematically. If you see, you're
Okay.
applying this Sx, that is, or phi x.
S of, yeah.
Yeah, which is a collection of all this low passed these.
Yeah, exactly.
Right? So this has all information, but not in a nice enough manner to invert it.
Right.
So you can invert from standard wavelet coefficient, even from the modulus you can get back to the signal. That actually even for STFT under some assumptions. But here, the moment you do this, you cannot usually get back
Back, okay.
to the signal exactly. But you can get, I mean, so okay, I can proceed to the next talk itself. So, but you can get back some approximation using some gradient descent, for example. So you can get
Right.
back a x hat. So that they have applied, for example, in case of texture recognition and texture generation. So you have, yeah. So you want to say model textures. It's okay for classification, but if you want to get back this texture, it gets very nasty, basically.
Right.
Because yeah,
It's a
Because
lossy
of the-
approach. It's
Sorry?
basically it's a lossy approach.
it's yes,
Yeah.
yes, information.
From an
Right.
information
Yes,
Yeah.
it's a
well,
lossy
yes, because you do have the information more or less, but not always. So if it's not an ergodic, which is actually what they show in the next paper that we're discussing, 2016 one. So if it's, for example, complex structure like a texture, it's not ergodic, it's not Gaussian, it's nothing. So then all this starts getting more and more lossy, like you said. So
Right.
the information is not nice and well behaved.
Because it's not invertible basically. So
Yeah.
you cannot, yeah.
Yeah, but if it's at least Gaussian or ergodic in a sense, then you can still argue that what you're doing is point-wise transforms. So it will still preserve ergodicity to some extent.
Right.
So
Yeah.
that's also what they show in practice.
Right.
In general, it does not, because you know that you don't have all these features that preserve ergodicity. You need to prove ergodicity, right?
No. So they don't prove it. It's just more or less hand waving that you put a linear transform point-wise and then an absolute. All this is point-wise. So it's like doing if it's Gaussian, then you can hand-wavingly say that
Right.
law of large numbers and so on, ergodicity. But there is no formal proof. But their experiments continually show that they can even recover in certain cases of ergodic signals. But if it's non-ergodic like texture, then there's no hope of getting back.
So ergodic and stationary,
Yes.
Yeah.
because you have frequency.
Right.
So
Yes, but actually audio is not strictly stationary. So
No,
it's,
no.
but
Yeah.
it's like quasi-stationary. It's that that's why it makes sense to do this localized wavelet analysis. So for images, okay, now I'm just combining both of them together. So images, it will look like something like this. So instead of 1D, you can take translation. So in images, what is something which you want invariance on? It is the translation, not just shift in X and Y. You want all kinds of translation also, like the, rotation also to be invariant. So you design filters that way. So you know that a wavelet will kill translation according to what it's designed for. So here, for example, it's designed to kill, in a way, this directional information. So even if you slightly tilt this, it should not give you a scattering feature which is too far apart. So the same argument as in the 1D case, if it's a little bit of shift, it should not go haywire.
Exactly.
So it's the same thing also can be shown for 2D signals or higher, the same thing. So the idea is to make it more and more invariant to this translation. So in general, lot of these variations can be locally shown to be translation. You can approximate by translation. So if you have something that kills small translations or ball of translations, so to speak, then that's of merit. But you don't want it to kill too much of information also. So that's why, from what I've seen, is that this transform makes a good trade-off. In that it kills some brings some invariance, but it does not give away leak out too much information. The MFCC actually leaked out too much information because you're using a low pass version, but so low passing actually kills translation, but you have also let loose of the high frequency. But by using this, you are capturing everything, but in a way building more and more invariant. So So for example, so in general, if you have inputs which are deformations of each other, so it's like these are the different inputs, for example, okay, belonging to two classes. And you can say model that one input is achieved by small deformation of the first, and then the small deformation, and so on. So it's like all the inputs. Look at it like the MNIST images. They are like small deformations of 3 in different shapes and so on, or small scalings and stretching. So if you can model like this. In principle, a lot of data can be modeled locally like this, but this, as such, you cannot draw a class, a boundary to classify. So you want to get a feature on X such that it looks something smooth like this, so that you can draw a boundary in between. Right? So and to do that, you must have some sort of invariance to translation. So that's precisely my point in the general sense. So you must have a feature which does not deform too much under small deformations. So you must have a feature vector which varies slowly if you know that deformations are small. So this might be in the feature space. So in the feature space, you might have a person sitting here, and the another input, the person might be sitting here. If you just take the MSE between these two, it's too far apart. But it's just transforming this person here. So it's actually this person, this image is nothing but a deformation of this image.
Right.
So you want a feature which actually tells that these are not far apart. And that was what ideally you want in general. So the deep scattering was only for time shifts. But in general, you want it for images, say for rotation, or in general, high dimensional input, it could be volume. You translate from one 3D point to the other 3D point. So you want a feature vector which builds this smoothness, if you know it's not too intuitively far apart. Actually, not even intuitively, mathematically. You can, if this is not too far apart. Or for example, faces. if you have different angles of the same face, you know they are not, you can actually put a 3D transformation and capture it. But then if you just take the MSE, then it's showing you too far apart. So you want a feature or a descriptor which is invariant to some extent. So that's what you want, and what you can show to some extent is that for nice enough deformations, the wavelet transform or the scattering transform in general will give you this kind of picture. So it will give you a descriptor which actually helps you linearize in a way, right? This is linearizing the input space actually. Or in effect this. If you have a deformation, then it should depend on the deformation, but it should not be too, I mean, if the deformation is small, then it should be small, or it should be lip stitch continuous in the deformation. And of all things, I think I have only seen the wavelet transform doing this business. But of course, this is under the assumption that locally you can express it as a translation and rotation, for example.
Right. Yeah, but that means like you have some assumptions on your feature vector, as you were saying.
On the input,
So,
as
yeah,
well,
on the
yes.
input, exactly. Yeah, that it satisfies this kind of like, it belongs to some sort of like low dimensional manifold. Linear in
Yes,
this case.
but you need not know it to some
Right.
extent, because you can, in many inputs you have so less data that you cannot conclude anything informatively about a manifold. I mean, if you have that, very
Right.
good, but if
Yeah.
you don't have that, you cannot conclude it. In those cases, you try to model local, what he calls local transformations.
Yeah,
So locally you can say it's a bit transformed.
but you don't need to know that a priori. You need that assumption to be true, but
Yes,
you don't need to know
you don't
what
need to
kind of-
know.
Yeah, exactly.
So you don't need to know what kind of tau, t, or
Yeah.
for example was. As long as it is not too violently far apart. So this, and why is it not important? Because you're doing all kinds of scales. So at one scale, one kind of variation is important. The other scale, the other kind of variation. So when you're building this whole multi-scale structure, you're taking care of all kinds of variations of the deformation.
Exactly.
So that is what I think intuitively is the picture, and that is also he explains. But beyond actually using the fact that the wavelet actually kills, that you can show mathematically, but in practice why it might work for any given data set is still questionable. But you at least have so much intuition that you can say that if it's not too far apart, then you know why it is killing, or why it is still doing better, because you have this wavelet structure. So the whole, one of the efforts of this whole philosophy is to explain or to understand why learned networks or why deep networks, for example, might be working. Because nobody understands what the weights mean, how the weights interact and so on. So the attempt to do this is to give some meaning on the weights. So like what we discussed earlier, to say that a deep convolutional network is doing something like building wavelet features. Because in practice, you do, actually that example is here somewhere, the invariance. So here, for example, so man with glasses minus man without glasses plus woman without glasses is a woman. So this is the output of not wavelet this thing, but it's a I think, I don't know which it was, I think it was Google or something, it was with Chintala. So this kind of behavior is observed, and people don't know why. So what you can at least say that maybe it performs, so if it's a wavelet structure, you know that it will happen. You can show to some extent.
Yeah.
So I think that is one way of looking about the importance of Mallat's work, that you can to some extent explain maybe this is what is happening in practical learned networks. And in many cases he shows that it's not so bad, but it's still not, of course, not matching the deep net, but it's still not very far apart in this image database. I don't know, was it ImageNet or something? That was CIFAR. Anyway, yeah. So it still gives, without learning, it still gives you 20% error. and the best learned network gives you 7% error. So this is still quite impressive because you don't do any learning, basically. So what would be of interest is to, for me, is to somehow incorporate an element of learning into this. Because I feel that this is too, indifferent of data. You can always somehow feedback data. That I have not really managed to think how exactly.
So you can definitely do better when you do something that depends on the data or whatever.
Yes, that is my guess. But this nice structure, of course, gets destroyed if you just randomly poke something here and there. And yes, and it does not explode. The dimension does not explode because if you notice, I told you that you have more exponential number of filters, but that's big. There is a step of subsampling because of this, nested structure. You can actually throw away every odd sample or even sample from this train. So in the end, it's not exploding much. The dimension is not exploding. That was what I think that I missed. So it's like this, for example, a huge initial image, and the second layer is 1 by 2. You throw every alternate sample. You can do that because it's a wavelet output, and you can continue doing that. So this would be your last layer up to the pixel level, and then you collect all these guys, and this is your feature vector. So if I had just done so this is the output of the wavelet. I'm just getting back to the wavelet explanation. This is the output of the wavelet. So this I take, this is the low pass version or the approximation. But if I just keep this, I would be doing something like the MFCC. I'm not capturing the high or the edge information. So I should capture this. To do that, what I do, I take the amplitude here and then low pass, and then I get these guys again and again. So that's what is happening. So I think I have pretty much discussed this part of it. So, and also in many data sets, like this is an example, the movement of the input or the translation of the input might not be important at pixel level, for example. It might be a group translating. So you need not actually keep track of each of the atoms. You can just keep track of a molecule. So that means you are grouping the information at different scales. So you can look this and slightly tilted version. You can look at difference from atom level, but that's already too. That's already too much effort. Maybe because they are coupled together, like in this example. The variation is in groups. So it makes sense, that's why it makes sense to see it at different scales. What are you doing by wavelet viewing? You're viewing it at different scales of activity. So maybe in this case, it's all that you require to is to view it in this high level instead of low level. So that's why maybe at lower, I said earlier that most of the information is captured in the high level wavelet layers. Probably that's because most of the data, exhibits some sort of local symmetries, what he calls, or local groups. So then the whole variation of data can be actually mapped to variation of subsets of groups of data, which also forms a motivation of using this multi-scale structure of this pyramid. So this was the paper, I think, where they show that if you add a small error, it gives you something completely different. I don't know if it's this. Yeah, so all these are classified as ostrich. So these are the inputs which were trained, and now you add a little bit of error around the edges, and
Right.
all these are, they look the same,
Yeah.
but they are actually classified by the system, by, I don't know which system it was, as an ostrich, which makes no sense.
Yeah.
So this is the kind of brittleness a lot of deep networks show.
Yeah.
But when you do this scattering transform, at least you can say that this will not happen.
Yeah.
So did they somehow optimize epsilon here in the ostrich direction, so to speak? Or what is it?
Aha.
Do you know?
Yeah. Maybe EWG. Is it EWG?
No, I think it was just, I'm not so sure, because they were not sure what is it in the ostrich that gives this. So, yeah, actually. And there was, it gets more interesting. So there are traffic signals of stop, for example. And if you just do a small occlusion here, it will give you a traffic signal of 15 kilometers. And there's no idea, I mean, that will be the output. So it gets more and more serious, this robustness issue. And
Yeah.
I don't think they understand how the change interacts to the.
Because of this, like the fact that perturbations,
But
and do not propagate well actually. Some, yeah, right? Or, yeah.
Yeah, this is again the same thing that a small shift will upset the Fourier coefficients. And another thing what he discusses is that in a non-ergodic data, even this is not sufficient, like I discussed. So this seems to leak out too much information. So then he suggests actually interacting, doing a sort of interaction among the layers. So currently it is like a wavelet packet.
You have to
Or
take
three.
combinations. I mean,
Yes.
Yeah.
something like.
So
combinatorics.
this, as such, the
Yeah.
scattering is, it does this and takes this guy, this chain.
Huh?
But yeah, what is probably the intuitive next step is to combine all this information in ways possible. So he also discusses that, but I couldn't get much how exactly he does it. But I think the idea is that you use all this information to get new layers. But then maybe it's not the wavelet structure anymore, but you can still use this.
Right.
For the non-ergodic,
Yeah.
but with not so
What's that?
such good results.
Yeah, it's not so good results. I think there is bias always to some extent. Yeah, I don't think they have solved it or anything. But in some of the more regular structures, they seem to do as well as at least using the Fourier transform, for example. I mean, by the argument that we saw earlier, this should obviously do better than the Fourier transform, because the frequency upsetting thing.
Non-ergodic problems are even unsolved information theory.
No.
One question. These psi and phi Lowpass filter and wavelets, how do they choose them? I mean, do they vary from the data set, or do they need to tune them?
So
for every
I think
specific-
most of the cases the Morley wavelet is actually used, or so the Morley wavelet, or the discretized version of the Morley wavelet. Morley wavelet is basically a Gabor atom, so it's the complex one. So it's I think in general it is of this form.
But you also have these frame conditions that I showed.
Yes.
Like
Yeah.
They have this kind of form, and they
Yeah,
use it for every
Yeah.
data set, and it works.
No, they have to have the frame conditions, as he said, as well, which I omitted. So it has to span the frequency spectrum fairly well. If there are leaks there already, then you cannot invert, and those kind of problems start coming. But yes, so of this form, this is a low pass filter, a low pass function. So it could be a Gaussian, and you have a exponential omega naught. So this is known as the Morley wavelet. So it is the real part looks like this, the Gaussian. So this you shrink, and this was actually the picture that I showed earlier. So this is used a lot, and there are a whole class of functions which have nicer properties that they kill polynomials, for example. So there are some wavelets which are known to kill polynomials up till a certain degree. Why is it important? Because if you have locally regular structures and then jumps, the wavelet will give you 0 here and only give you this. So that's why a lot of wavelets, most wavelets exhibit this sparsity. They will only identify the singularities. So all the information is actually singularity information. But in most of the analysis, I have not seen very data-specific choice of wavelets. I think it could also be done. But generating a wavelet for a particular data set is, I don't know, it's not very well explored. So I think that was pretty much what I had to conclude. If you have questions more regarding the math, you can discuss.
Just maybe some discussion, but I also had like maybe something that you could probably comment on, because apparently this idea now, this is kind of like a little bit contradictory to deep neural networks, right? So in neural networks, you're doing the training based on everything is data dependent. So your training changes significantly when you do during the training phase. And then you see this kind of like separate line of development, which is like everything is fixed, and then you try to express everything as a more deterministic in terms of embedding.
Indeed.
Yeah. So what do you think about each of them? Like, what are the pros and cons of each?
Of course, the most, I guess, intuitive way now is to learn everything from data as much as possible. But, it seems to have certain problems, like what I showed.
Yeah.
It seems to be too fragile in certain cases, and almost if you have, for example, self-driving cars which have been trained like this, and it sees a stop and goes ahead with 15,
exactly.
It's problematic.
Yeah.
But and I come from a more classical signal processing background, so I'm biased to like this formulation. But of course, I had sort of made peace with the fact that these things are not going to return, but it's somehow returning this way, and it's interesting. And the best part is that you don't have any of the numerical troubles involved with training. So if you go beyond 5 layers, already cross-validation and back propagation and whatnot, so they have all kinds of troubles even if you start too deep.
Right.
Unless you're Google or Facebook, then you have a lot of resources. But that way, I think that is the best selling point, if you ask me.
Yeah,
it seems to work okay, or at least pretty decently well.
Exactly.
In its current form.
Tractable.
Mathematically tractable. At least, that way the good thing is that you can assign a meaning of what is happening.
Yeah, exactly.
To it.
You can when you have something wrong that goes in your...
Yes,
like
you can to some extent
exactly.
troubleshoot, or
exactly.
you can expect that this is the wavelet, so this kind of behavior is what is happening.
Exactly.
But the other way, of course the thought process is the other way. So they want to explain that all networks are doing this kind of thing, which which I think is a bit far-stretched. I'm not so sure how.
Right. Yeah.
Yeah.
Yeah, but I guess maybe the drawback of this approach is like it doesn't do as well as the other.
No.
Yeah, exactly. But I mean, like,
And it has some
It's-
regularity assumptions, whether or
Uh-huh.
not you like it.
Mhm.
So it
regularity on the input.
on the
side,
input,
yeah.
on the input. So, like I said, it is diffeomorphisms and small translation and scaling. But if it's too far apart, then of course, like anything else,
Yeah.
this probably won't capture.
Mhm.
And probably this will not capture all the more because this is built on that kind of invariance of
Exactly.
wavelet structure.
Exactly.
So if it is
Yeah.
too far violently away from the basic regularity, so you do, like I said,
Yeah.
all this proofs of that it does not go too far away actually relies on certain regularity on the input.
Yeah, and I mean that's true of like any classification, right? I mean if your classes, if the inputs are like, as you say, widely different, then there's probably not much we can do anyway. Yeah.
So the good thing is this is almost immediately implementable. There's a very good, it's almost like a repository here. They have the codes, they have the recent papers and everything. So the first one, you can check
Right.
that out.
Yeah.
And the code is quite simple. I did not really try running it for this presentation, but I did try running it. It's not, I mean, it's very fast.
It's quite fast. Yeah,
I
exactly.
don't have
Because
to
there's no
learn
training.
anything.
Yeah.
So this is basically the paper that I considered, and this is where he first introduced that thing. So this is slightly more mathematical, in the sense where he actually proves the wavelet translation invariance and so on.
Right. Yeah.
And what was interesting is that they went on to use one of the wavelets that I proposed in the
Really?
masters
Okay.
to also do. I think it's there in the package.
Nice.
Which is nice.
Yeah. That's gonna be a nice reward if Mallat uses.
I mean, it was nice that
Sure.
the student of Mallat says okay, and then they even include it in their article, I think. But then I would want to use this because I said it has a lot of less training phases. But then I would also want to incorporate some feedback
Yeah,
from the data
right.
because it is intuitive to me that using data structure, because this is, although using sort of regularity on the input, it's not actually using the input from the training set.
Exactly. Just
So
as,
maybe
yeah.
that would be better.
But then, yeah. So
How about, I mean, have you seen any of the papers that uses a linear classifier at the output of the filter extraction? Because already doing SVM is sort of a second feature extraction step, right?
Right.
So have they tried, or have you tried with linear classifiers, more simple stuff after feature extraction?
No, I think they have done a simple discriminant. I mean, they have done that as well. I mean, SVM was only for this
Okay.
article, but I mean, in principle, what they say is that this is a feature vector. Now you can do whatever you want with the feature.
Of course.
yeah.
Just that it has this. So that is the, sort of the take-home, very unjust message. But yes, that this
Yeah.
feature is robust to a lot of things, and it's sort of contracting your degree of freedoms. So
Yeah.
in a way, like what we saw. So it's making it invariant to a ball of variation, but still keeping enough information that you can distinguish certain classes.
Exactly. Exactly. Yeah.
But here again, then I don't know if you give me a different data set, whether this will do well. A new data
Yeah,
set.
right.
I mean, so that question is something that I asked. I don't know, even in this, because to some extent you would expect that if it's so deterministic, you can comment. I don't see such arguments. That
Right.
Well, you do have a mathematical condition, right? Like, well, if it's regular enough, it will work. Yeah. It's more than.
Yeah. Because I mean, like ultimately everything is assessed by how well does it do on
Yes.
numerical experiments, basically. Yeah.
But that is also
but
saying that there is minimal assumptions on data, but it still uses some sort of structure. So,
Yeah.
but there is no argument to saying okay. But that is also true in general about wavelets. That wavelets, although it's a nice tool, it has not been used in audio, for example, as much as in video and image, because it somehow sparsifies images much better than it sparsifies audio for some reason, but nobody knows why. So
Right. Yeah.
I guess
Yeah.
images are more regular and audio is more
Right.
less stationary on a long time.
Yeah.
So what Mikael presented last time is this, the generalization of this. So instead of a wavelet basis, you just put a general frame.
Yeah, exactly.
So which actually is much more general, I think, but that makes it much more intractable.
Right.
Because
And-
wavelet is well understood. Frames, not so much in my understanding.
Yeah.
It's
No,
understood, but
over there, exactly, in the paper that Mikael presented as well, like also there's no training. I mean, you just like compute
No.
these coefficients, you
No.
fix them in advance, and you just do convolutions.
Yeah.
That's it, basically. Yeah. Right.
and so
Yeah.
I hope at least this was made across that the averaging is to kill some sort of translation. So where
Yeah.
where exactly it does not matter if you just average. But if you just average and
Yeah.
use it, you have lost some information. So you want
Yeah,
also
exactly.
to retain. That's why you have the
Yeah.
high frequency component. But you don't take it as such. You want to
Yeah.
still cut down its variation because it will be too
Mhm.
oscillating. So you put the amplitude.
Yeah, exactly.
And the amplitude is contracting operation. So that also
Mhm.
adds to the contraction property. So
Right.
this much is what you can take away intuitively from
Mhm.
this thing.
Yeah.
And it matters on what, how many scales you use also matters. That matters, and that nobody can
Yeah.
tell you also. But it's at least okay that you don't have to learn from it. Or maybe you should.
Yeah, but I mean, like definitely, like less things to learn, to adapt than like neural networks in
Yeah.
general. Yeah.
No, I'm not advocating this being replaced with
No, yeah.
but you can't. I mean, even he does not advocate. I mean, just that this probably gives you an insight. Because everybody is like, okay, this works, but why does it work?
Right.
So
Yeah,
maybe,
exactly.
maybe. That's
If
it.
if it did work like that, those other things wouldn't happen, right? The perturbations wouldn't be possible.
Yeah.
So
Right,
it's,
and then you
it's
wouldn't-
self-discarding. It doesn't work like that. It's
Yeah, it
true.
doesn't. Yeah.
Yeah, but then, as you said, like it also means that probably, I mean, if there is an equivalent between this and neural networks, then probably it means that training, all this fuss about training, like propagation, at some point you're probably not gonna need that. At
No,
some
but
point in
yeah.
the future, yeah.
And also,
Because,
I think that point is good that you should probably use this while you train normal deep network somehow.
Mhm. As like a-
so that you,
yeah.
this robustness problem, I mean, you ensure this contraction
Mhm.
property, which is very
Yeah.
nice. So if x
Yeah.
and x dash are not too far, then the features should not
Mhm.
be very far. But it's not the case in the deep learned features.
Exactly, exactly, yeah. So yeah, I mean, I think both are like kind of complementary,
Yeah.
yeah.
And I realized this was too much to do in one session only after I started
We
preparing.
can probably actually pick up this work later, actually, so Mallat's paper.
We could.
Yeah, the one that you started, pick it up later, actually, talk about it in some other session.
Hmm.
Yeah.
Thank you.
Thank you.